Okay, so our second speaker today is Ricky, who's a fourth-year maths student with loads of experience in reinforcement learning and is going to create more large driverless cars, I guess.
Thank you. Yeah. Again, I think most of you know me. I'm Ricky. So today I have three sections to my talk. I'm going to take you through some background in reinforcement learning and motivation why this is an important problem. Then an experiment that I did run and some of the results from that, and the experiment that I'm literally currently running now. I have participants coming in the morning to do the experiment. So we're going to start with some background. We're mainly going to be talking about reinforcement learning. We'll get back to the pedestrians and the vehicles and stuff a little bit later. But now I have the task of explaining reinforcement learning in 2 minutes. So bear with me if it's not all that clear. I have a nice little graphic stolen from a great website that you should definitely look if you are interested in how reinforcement learning works. So here we have an agent. That's our little blue dot you can see bouncing around up there. And he can be in any state, which is a square. And he can go from these states, and he's trying to get to the green state and not end up in the blue state, the red state. And we can model that with a temporal difference learning method, where we say the value of a state is equal to the reward of the next state plus its value to normalize it. But we want to take that a step further, and we look at something called Q-learning, which is where we don't only look at which state it's in, we look at the value of an action too. So we say that each triangle in our square, so that relates to the action of going up or left or down, they also have a value, and that the value of this state is equal to the value of the next state and its best action. And then we propagate that backwards, which you should see, as you will see some of the green starting to bleed down as we iteratively run this through multiple runs. We're giving more and more value to these actions in the states. And from that, we can build something we call a policy. We call that pi, which is basically the expected total return or expected total reward that we're going to get from taking those actions in that sequence of actions we're calling our policy. Now, when we're dealing with things like driving, either in real life or in a simulation, you end up with millions and millions of states and actions that you can take, and it's just not feasible to hold the number for all of those and keep track of them. So instead of actually solving those equations, we create a loss function, we use a neural network, and we have that hold the function and output. We give it a state, and it tells us what the value of that state is. There's lots of tricks that we have to pull to do that. So we have to some way even out the exploration versus exploitation. How much should we keep sampling something we know is good to converge on our value, versus how much we explore in states where we don't know if they're good or not yet, to see if they might be better than the one we already think. So we take advantage of things like batch sampling and replay memory. So batch sampling is we do a bunch of things in the environment and then update our neural network. We don't do it after every action, because if we do it after every action, we're going to have to train our model. For one, it's just sample efficiency. And the replay memory is how we save all of those actions, so we don't have to do that all online. So in my case, I use a simulator, and I don't want to have that running and make an action and let all that code run and bring it back every time I want to update my neural network. I let it run for a bit, then I stop it, take all of those actions and update my neural network with it. There's some more, how would you say it, some more technical details to exactly how that works that I'm skipping over, that you have to use policy gradient for how to work. George in the audience here knows all about that, so you can ask him all about policy gradient.
Don't feel obliged.
So, what I've explained up to now takes us down the main path on this flow diagram I have. So we have an environment, our driving simulation, observed data from the real world, whatever we have. And then we need to define some way to tell the agent what is good and what is not, because in the world we don't have a nice green square that we know we want to go to. We just have, maybe a destination. We have to work out how to define that, and we may have to define things that are good along the way, i.e. don't hit pedestrians, don't drive off the road, that kind of thing. So the main part of my work is defining how we do that when we don't know exactly what we should say to the agent is good or not, because we just don't know what it is. What constitutes good driving is subjective. Nobody actually knows what that is. So in some way, we have to collect data to find out what that is, and then reincorporate that back into our reward systems. Next slide. Okay, so as we do that, we need to evaluate the policy. Is this actually a good policy? We've given it this reward and told the neural network by numbers that it's good. Is this actually good? And there's several, this is from a great survey paper, that there's several things that it can do that you don't like. It learns loopholes, it learns to match what people like by the exact feedback mechanism rather than the thing they're trying to express that they like. Or it has more or less attributes than it should, so it doesn't learn what it should be learning. Oh, we do it for time. Okay, so that should take us into the first experiment. So here I've used a simulator called SMARTS. I do not remember what it stands for. But this is wrote by a team at Huawei. They made this big simulator that you can do all of this. I had to put the pedestrians in. I had the assets, but they hadn't implemented it yet. But as you can see, it's a real cool little simulator. I've spent hours watching cars almost hit pedestrians on this. But the good thing about it is it's based in Python. It has a JavaScript front end, which I hate, but most of it is based in Python. And those of you who've done any machine learning know that almost all machine learning code is also in Python. So that's a nice way for me to be able to connect them up together. And it provides me with all sorts of observations. The way we're defining our states, it tells me where the car is, how big the car is, where the roads are, how fast things are going, what other entities are there. It just tells me everything it possibly can from this simulator, which is great. This is all the information I need to know. And it provides me with a reward function. It has an internal checkpoint system, and it tells me, I tell it where the car wants to go, and it will give me a reward back from that. But as we argued, that's not everything we want to see from the car, right? We want to elicit behaviors that feel better, that don't have things that we would call something like a computer move, something that doesn't feel human-like. If something does something weird and it's unpredictable, people don't like that. So we want to make it do things that people like, and just rewarding the car on getting to its destination doesn't necessarily do that. So we're going to investigate what people think about that. And the simple things to do is to code up an algorithm, let it play in my simulator, and then ask them what it is. And that's exactly what I did. This is on something called Qualtrics, which is like a survey software that I did during the middle of lockdown. I sent this to a bunch of psychology undergrads that filled it out for me. And then we're going to have a look at the data and see what we can improve on. So this is examples of the kind of things that I was showing them. So you might think that that's not very, you don't really want your car doing that, even if it gives it a good reward by what Smart says. Oh, I didn't know I was going to show you my recommended. That's fantastic. And on some of them, I stopped it early and still asked them what it is. Oh, I got too many times. There we are. So yeah, there was lots of results, lots of things I looked at in this. There was, not only did I have it stop sometimes, I actually showed them when it hit a pedestrian sometimes and asked them what they thought about that, which pleasingly they didn't like. So that's good, because when you talk to psychologists, people don't always do what you want them to, or things that you think are very evident, they don't agree with. But basically I had 4 different models, 0, 3, 5, and 10, and that relates to the amount of like simulation meters that they would start losing reward. So if they're too close to the pedestrian, I'd start taking their reward away, telling them that's bad. Thinking that if they give the pedestrian room, then the people are going to like that because they feel safer. Wasn't really what I saw. I saw the inverse. So lower ratings down here with the more bulbous, it shows that they rated them lower. So the ones that stayed away further, they rated much lower than the ones that stayed closer. So we had to think about that some more and why that was the case. So after doing way too much data analysis in Jupyter Notebooks, trying to figure out all of this, is that we found a correlation between the average rate of vehicle heading change, which is a very papery way to say how much they were steering. So smooth trajectories, cars that stayed in a nice straight line, had a much better approval rating, that's the word, than cars that moved about. Not so much the case, the green line is where I stopped it beforehand, but this was also correlated in a graph that I'm not showing you with how close that was then related to how close they were to the pedestrian. And you can, I'm not sure if you can see, because all of the vehicles down here had a big change in their steering, which means they steered into the pedestrian quite hard and then hit the pedestrian, which is the consistent ones. And they really didn't like them because they like in the lowest amounts, because the Y is how high their approval rating is. So it's good to see them way down here, which is something that did work at least. So this is a great first foray into it, start looking at what people do. From there, we want to design an experiment where we can show how we can improve it using these data. So I moved away from smarts, great as it is, because A, it's very computationally heavy, and B, I don't have control over a lot of it. I mean, the code is there, but there is thousands and thousands of lines, and I don't want to read through it all, and even if I did, I wouldn't understand it in the way that somebody that wrote it would. So I wrote my own simulator in a package called Pygame. If any of you have seen it, it's very simplistic. It's basically a grid world, you put images over it, and it looks lovely, but the pedestrian and the car and the roads are basically like 4 boxes in a big box underneath the hood. The pretty images make it look nice, but that's all it is going under there. And this allows us to not only have much simpler data, have control of everything. It allows me to give control of the pedestrian to the participant. So now they're not just watching clips of what's happening, they are actually in control of that pedestrian and can move him around and cross the road themselves and give me feedback in the PsychoPy package, which is this nice grey box thing, and I can elicit feedback from them and save it from this, and this is all happening locally now in code that I understand and can keep track of. So this is how the experimental procedure works. I have an intro page, tell them what they're going to do, and then for each trial, I have like an initialization page, and I get them to interact with the agent and its policy. Then I ask them about this policy, and then I get them to do it again and again and again, like 75 times, which I'm sure they're going to enjoy. But, so I've spoken about this a lot, so let us actually have a little look at it working. Yeah, I mean, it was working 10 minutes before, and it would take a couple of seconds to load. Don't judge my code. So okay, yeah, so this is the first thing where they have handouts. There's all sorts of psychology experimental procedure that goes with having to do this with real people. But give them a quick sort of intro into what they're doing. And then I get the simulator working. And there's a little car, and this is me on the keyboard controlling my little guy around. And then I can run him into the car, and he's like, oh, no, we don't like that. And it ends. And then I do the same. I ask them, to give me feedback on how well they did on these 3 things. So these 3 things that I'm asking about are very important because, oh no, Dex doesn't work, have to escape. There we are. Go back to this. I did try and incorporate this into the PowerPoint and it didn't work very well. So yeah, this is an awful slide that's just full of stuff. But this is how I've made the reward. This is what I've shaped the reward to be. So ask them about those 3 things: the speed, the position, and the steering. And this relates to the way I've defined my shaped reward here, which is the speed, the position, and the steering. And they're all normalized by the maximum values to put them between 0 and 1, and then a -3 off the end to make the reward always negative. So 0 reward is the best reward they can get. This is just parameters defining what total expected return is and how I'm defining a trajectory. But here is the key point, is that I build this utility function around it, parameterized by these thetas, where I've rearranged this a little, where I say that the total expected return is related to how they give me feedback. So if they give me high feedback, I take this to integer powers. If they give me low feedback, so if they give me negative numbers, I take it to 1 over n feedback. So we can have a look at that here. So for each term, the x equals y there relates to an exponent of 1. So that would just recover that shape of reward for me. But you can see here that each of the different responses that they give me on that I think it's called a Likert scale. On the Likert scale relates to me either sort of making it concave or convex, the reward function. And this one, I've called it density shift. I'm not sure if it's the true density or not. But this shows that for low values of theta, I have much more effect. I lift up the low rewards, encouraging exploration. If I say this state that you thought was bad is actually a bit better than you thought, it's going to go back there and look at it some more. And for the opposite case, when it says it's good, I bring down the values. Is that true? Or have I got that backwards? Yeah, no. So yeah, I show that it's more effective on the high rewards. So the amount that high thetas bring up the reward is greater than the amount that low thetas bring down the reward when it's above 0.5, meaning that it cements in the policy. I showed you some actions, you thought they were good, so I'm going to increase the rewards for those to make you even less likely to do anything else. This is what you should be doing. So that's about it. I'm in the middle of showing people trajectories, showing people these policies working and getting their feedback. And then I had to basically train like 300 models to show all of those different parameters, or the combination of all those different parameters. And then whatever they say that they like about it or don't like about it, I show them the corresponding model corresponding to the parameters as we set them out. And we'll see how that goes and whether I can see any positive correlations or if they just don't do what I think they're going to do again. But from there, it probably won't be me because I'm, as Jack said, a 4th year. But what we want to do is look at the behavioural experiments and find out if these judgments are actually effective. Because there's lots of work on preference data where you ask a participant, is this trajectory or that trajectory better, rather than an objective judgment of is it good or not. And we want to show that the effects of that are there and are true and are psychologically significant. We want to use those to infer from the assessments. We want to infer whether the interaction was good or not, and whether it was the person or the car that did something bad. And yeah, take it into a multi-agent domain where the reinforcement learning agent isn't just giving rewards for states, it's also aware of the other entities in there, and that's part of its states. And that's so we could then give it an intrinsic model of the pedestrian, and it would be more adaptive to pedestrians that have different preferences and therefore give different judgments. So yeah, I'm a little early, but I think that's about me. I don't have a question slides, but thank you for your time.